Hello, hi, my name is Mohammed Rahmani, and today I'm going to show you how you can load your own raw EEG files recorded using other systems and other software like OpenBCI or Emotiv into OpenVibe, so reformat it in a way that OpenVibe likes, and even use your own markers and modify them to be compatible with OpenVibe. And we're going to run a motor imagery scenario as an example, but it can be used for any variety of paradigms that uses markers to communicate the events. So let's see. We're going to start with, well, you can download OpenVibe from their website, openvibe.inria.fr. And we're going to use the latest version at this moment, 3.3.1. You can just go on their website. It's an originally for Linux, but there's also a Windows version. That's the one we're going to use today. So when you install it, OpenVibe has two important parts that have to run at the same time. One is the designer. The other is the acquisition server. Let's open the designer first. Right. So this is the log window. You can keep it open. There's also a log window here, but this is more verbose. And this is the, well, let me open a scenario to show you. This folder icon here says open an existing scenario. By default, opens the built-in scenarios that come with OpenVibe, and which is one of the strong points of OpenVibe. It has all these scenarios for you to try out. And we're going to use this one, motor imagery CSV. And most scenarios in OpenVibe, they have this step-by-step structure, which is great. And motor imagery is one of the scenarios that pretty much works out of the box without much modification, in contrast with the P300 speller ones that are really hard to make work. So let's open the signal monitoring one. This is the design environment in OpenVibe. It's a node-based environment, and you can add more from this right-hand side section. By the way, this can actually be hidden, and I have no idea which button opens it up, so just know that it might be here. You can add other boxes here. You can browse them or search for them. For example, I mean, we're gonna read a CSV file eventually, so type CSV. See file reading and writing. And there's a CSV section. There's a file reader and writer. You can click and drag the reader, and each node has types of inputs and outputs, and you can hover over them to see what they are. And we're gonna see how all of this works. Just remove this, delete. Now let's just open the acquisition server to, by default, right, this is a log for the acquisition server. I put that here. So by default, if I try to run this scenario, nothing should happen. Yeah, it'll throw me an error. By the way, we're going to see a lot of errors and crashes, and I'm going to show you how to deal with all of them. So it's going to crash if the acquisition server is not running, because here you see this whole scenario begins with this acquisition client node, and this requires the acquisition server to be running. And you can see in the errors here, tells you could not connect the server, make sure the server is running and in play state. All right, so we're going to do that now. This is the acquisition server, and here you see all the different devices and even network streams that OpenVibe can connect to. If you have any of the devices, you can connect it. We're going to try OpenBCI today. but you can also use their lab streaming layer. It is unstable if you abruptly close your stream. OpenVibe Acquistion Server will crash, but it works. It's functional. Just have to be careful. We have an OpenVibe, an OpenBCI Cyton+Daisy module here. I'm just going to show you how to turn that on if you happen to have one. First, you have to make sure the switch is on the GPIO side. So this can switch a lot, and just pay attention. It could be just frustrating if you don't know. And we plug that in. There we go. Blue light. And if it's plugged in, you can just switch this up. Up is for the radio module, which is this. And down is for Bluetooth, but not even sure if it works. So it's on. If you have installed the GUI on your computer before and know how to run it, this should connect with no problem. Here we can just check the driver properties. First, just make sure which USB port the Daisy module is connected to, so we can find that in Device Manager and where is it? There we go. Yeah, I mean, it's the one port. Yeah, so it's COM4, but if you have many, you can just check here to see. You can connect it and disconnect it and see which one shows up. So yeah, there you go. And you can use the Daisy module or not, doesn't matter here. And apply. Connect to port 1024, pay attention to this, and sample count % block, it's 32. We're just gonna keep it that way. Just pay attention to this, we'll come back to it later. And click connect. Connection succeeded. And still, if I play here, so now it's playing, but nothing's showing up because we haven't clicked play here. So stop that. Yes. Play. And it crashed. It's okay. It's okay. Don't panic. Happens all the time. So let's try this again. Acquisition server. This is a good thing about it. I can just run it again. It's in that way resilient. Everything else should be the same. Oh, by the way, let me just have this here as well, because one way to know it is streaming is to see the red light go on. So just make this smaller. Does it? Oh. Okay, that's strange. This connection, so you see the red light. That means it's streaming, but it's just not sending the. This means the headset is sending signals, so it's just the server not sending them to the designer here. So put that here. Oh, and play. Now it's sending. And now if I press play, there we go. So here you see two signal display windows, the ones depicted here. Filtered signal shouldn't be called filtered signals, should be called raw signals. Oh, I didn't notice that. But so this one going directly to the signal display. Well, this is confusing. Let me just let me stop that. You can just select the connections and delete them. So this one go like this. All right. Now let's try it. Yeah, it makes more sense now. So you see, like the raw signals are just going directly at the similar inputs for the raw signal window here, and the filtered ones going through a temporal filter. This one is, I think it's let's see, yeah, it's a 1 hertz to 40 hertz filter, 4th order bandpass. So that's the filter that's applied to them here. And yeah, I can maybe touch it, make sure this is a signal that we're getting, yeah. And yeah, this is how the scenario is run in OpenVibe. Now, let's record some signal as a CSV file through OpenVibe to see what kind of structure it records as, because it reads its own CSV file. So if we just take a look at that, we can figure out how it works. All right. Stop this. Disconnect. So the idea here is that in the end, we're going to be able to replace the acquisition node with a CSV file reader node and have a CSV file that is compatible with this CSV file reader box, because you can try it. I mean, wouldn't be able to read any other format. So you can actually go to the box's documentation. So each box, if you right click on it, you can, here. It opens up the documentation for it, and this is the best way to do it, because if you look it up on Google, you'll hit all the different versions of each box. And it does have a guide on what the structure should be, but this is actually, I couldn't use this. And in fact, the file that OpenVibe records itself is not similar to this. Kind of is, but it's different. I'll show you. So first, we're going to remove this. I'm going to put a CSV file writer here, and we're just going to click connect acquisition client to the relevant inputs in the CSV file writer. And then you can double click on it. Here you can check the properties of each node, and we can select a location for it, desktop. All right, and let's run the acquisition server again. Let's see. Lower the exposure. All right. Properties. Yep. Use Daisy module. Apply. Connect. Play. Play. These are the rest of them. It's good enough. Stop. Disconnect. Let's use. All right. So this is the file. It's a CSV file. CSV stands for comma separated values. And this is basically a spreadsheet with each element separated by a comma. So these are basically headers for each of the columns of data that we have. And this is the file that was recorded directly from the acquisition client without any manipulation. So this is exactly how it reads and writes the files. So here, if I bring a CSV file reader box, and let's just directly replace these. And the filter as well. All right, and can go ahead and disable this and this because we're not gonna rewrite it. And if we point it at our file, we should be able to play it back. There we go. With no problem, and also fast forward through it, this button here. And so this shows that this is how OpenVibe prefers to read and write CSV files. And again, if you go to the reader or the writer documentation, the format is explained here, but what's shown here does not match what we just made. So it says time, channel 1, all the channels and sampling rate, but here we, if we zoom out, yeah, here we have time and sampling rate, and then epoch column we don't have here, channel 1, and so this doesn't match. There is a description that it matches with. If you look up OpenVibe CSV file format description, there we go. So here you can find the correct documentation. It is an older documentation here. So it's September 2017, and the one we opened from the designer is more recent but incorrect. But this matches with what we have. So you have time, and then the sampling rate. Then you have epoch, as we have here. And then you have your channels. They're named there, but they could be named anything. And so we have, it was a 16 channel recording plus 3 accelerometer channels, so 19 in total. And then we have the event ID, event date, and event duration columns as described here as well. There's also a good reference for other stream types that OpenVibe has. So if you wanted to convert other types of data to OpenVibe, you can refer to this file here. But we're gonna go through each of these columns one by one ourselves and explain what the function of each is, so we're able to convert any other recording to one that OpenVibe can read. So let's, for comparison, also record an 8-channel file using the same setup. So OpenBCI with the Daisy module can record both in 16-channel and 8-channel mode. We can undo all of this. Let's disable this and new file 8-channel. So when you open the acquisition client and go to driver properties, you can uncheck this here. See, it says, if I check it, 16 EEG channels, 3 accelerometer channels, and 125 Hertz sampling rate. And when you open in 8-channel mode, by default, it will record at a higher sampling rate, 250 Hertz. This is due to the radio limitations between the dongle and the headset, plus the 3 accelerometer channels. So everything else is the same. Connect. We're connected. Play. And we need to enable this, disable this. There we go. Press play. All right. Yeah, here we have 8 channels plus the 3 accelerometer ones. Maybe touch one. There we go. And that's good enough. Stop, disconnect, and we go to desktop. There's our file. So for all intents and purposes, these two files are recorded with 2 different devices, although they're done both with OpenBCI, because one is 8 channels and recorded at 250 Hertz. The other is 16 channels and recorded at 125 Hertz. And these two are the most important difference between recordings in OpenVibe. Other than that, if you look at the files, they're not much different at all. The headers are very similar. They follow the same structure shown here. So you have the time column, the epoch channels, and the 3 extra columns, event ID, event date, and event duration. But other than that, you have mainly your channels and your samples. Let's look at them in detail, this time using a spreadsheet program. A channel. So this is what a CSV file actually represents. So if we compare it to the text file, remember that CSV files are text files and they have to be converted to a number. Otherwise, these two are exactly the same, just that the commas separating each column is now replaced with an actual table. So if I, example here, I add hello and save, should reflect in my text file. Yeah, here. All right. So yeah. So let's read that. So you can see that other than the number of channels, the right-hand columns don't seem to be that much different. So one was 8 channels and 3 accelerometers. The other was 16 channel and 3 accelerometers. And they're really not that different at all. The only difference is in the first 2 columns, time and epoch. So for the time column, this is the first important difference, of course, is the sampling rate. So all OpenVibe CSV recordings would start with capital T time, colon, the sampling rate, and capital H and small z for Hertz. And then you have the timestamps under it, which is standard for any sort of biomedical or any time discrete signal record for that matter. But the ones in OpenVibe, they don't seem to correspond to the actual recording time because they're auto-generated for each recording. And I'll show that to you in more detail later. But that's good news for us, which means you really don't need to have a timestamp for your recording, and you can easily auto-generate it yourself for your own file. The other important column is the epoch column, which should honestly be called the chunk column instead of epoch, and I'll tell you why in a bit. But let's just take a look at it. So it starts with 0, and at the 30-second sample, it switches to 1, And at the 64th sample, it switches to 2, and so on and so forth until the end of the file. Same with the 8-channel file. So where is this coming from? If you remember from the acquisition client, we had this sample count per cent block parameter that we didn't touch. By default, it was set at 32. But this is what determines what happens in the epoch column. So OpenVibe strictly works in chunks of data, and it's actually very sensitive to these chunks as well, and always expects complete chunks in the file. Other than that, it would crash. You can actually see the chunks in real time. Let me connect again and play. Oh, it's trying to overwrite the file. Let me disable this box. All right, now it's not writing to anything. So yeah, you see that the data is not coming one by one sample. Well, let me maybe use a larger block. Let's say 256. Right, now you see it's coming in larger chunks. And that's just how OpenVibe is designed to work. It always operates in blocks and always expects the same number of blocks for every recording. And as you can see here, there is no difference between a 250 Hertz sampling rate file or 125 Hertz. It always sends the same number of blocks based on what is designated here, and the device doesn't really make a difference, which is also good news, because that means we can also easily create our own epoch column, but we just have to make sure that they end with a complete block. Otherwise, OpenVibe will crash when it reaches the end of your file. But the timestamps do follow a different structure. So for the 250 Hertz file, you would expect to see 1 second pass after the 250th sample, which it does here. And for the 125 Hertz file, the same is true for the 125th sample. There we go. But other than that, they are growing at their sampling rate. So if I open calculator, see 1 over 125 is 0.008, which is what we have here, the second sample. And if we divide 250, I'm sorry, 1 over 250, we get 0.004, which is exactly what we have here. So they are different in that way, but there's honestly nothing complicated about it. And you can easily recreate this with a simple Python script or using NumPy or Pandas. But other than that, there is no difference between these two files. And if it's not designated here, OpenVibe has no way of telling the difference between these two files. And in reality, that's the nature of all EEG recordings. So if we were to record using OpenBCI's own GUI, the raw recording will be this text file, which is another CSV file. It has this header, which has details about the recording. Now, if I open it as a spreadsheet, you see that it has this sample index column, which is just numbers growing. And you have your channel data, which is the main part of the recording. And then you have all these extra columns from other sensors on the device. And there you have an actual timestamp column in 2 different formats, which of course will not have the neat distance between them, but they really wouldn't matter in the end, because at the end of the day, you have samples that are assumed to be taken at regular intervals. And the speed that you recorded it would be the speed that you would play it back. And that's the heart and soul of any sampling. So let me show you. If I just go ahead and delete this column and delete these. And oh, we need an extra column here. And copy the header from this file. And we don't need any of these. We don't even need the accelerometer channels for our purposes today. So we can just get rid of these columns. Let me repaste the, oh, let me copy the time and epoch columns. There we go. So it wouldn't reach all the way to the end because it's a much shorter recording, but it'll do. Delete. There we go. Well, I don't know how these got smaller, but I should just add these 3. Got deleted. There we go. And if I save this, we should be able to just read it with OpenVibe. So let me enable this again. And now if I choose the file we just saved, there we go, play again. Oh, something's probably wrong with the file. Let's see. Ah, yeah. So you see these extra commas, they shouldn't be there, and it's no problem. CSV file is just a text file, so I can just edit it as text. So I think, yeah, well, if I find this, we can replace it with nothing. There we go. Still have these left, 3 extra ones, because these are the 3 empty columns. So this should be okay now. There we go. Isn't that great? So this is a file from a complete different system, although the same device, but a complete different software saved it. We got it from another file. We just changed the header and added 2 extra columns. And now it's being read as a native OpenVibe file. And we can even do the same with the file recorded with a completely different sample rate and device. So we're going to also convert Emotiv Epoc files. If we look at the raw files from them, it's also another CSV file. So if we open it, you can see it also has different columns and channels for things. So it starts with timestamp, but the actual signals from channels start here. But I can go ahead and just pick any 8 of these channels. And let's see how many we have. 3,200. So I can just go ahead and let's say 7. 1, 2, 3, 4, 5, 6, 7, 8. And we can just pick the samples directly and go down to 3,200. Just about. And just copy. And go here and replace the ones here. There we go. It should exceed by, yeah, so about 20. Let's just get rid of it. Let me just remove the row to make sure it's not making any extra commas anywhere. But yeah, this is now, this should be read with no problem. Let me save it as a different file. You could save it as CSV or text, doesn't make a difference. And if we go to OpenVibe, pick our new file. Let's look at it as a text again. It also has the extra ones. All right, should be good. Save. And now it's playing. So this is a signal from a 128 Hertz device, a complete different device. We just picked the samples right out and replaced it with the ones we had already in our file. And it's reading it no problem. Because again, other than this header and what's in these 2 columns, OpenVibe has no way of knowing the difference between those files. They're all just samples in time. And that's what all EEG files are. They're all just spreadsheets with different headers. And you only need your samples and know your sampling rate to be able to work with them. Because although this is playing, but this is incorrect. We shouldn't treat a different sample signal 128 Hertz here as 250 Hertz because all the filterings and all the processing would be incorrect. But this is just to demonstrate the simple nature of how things function under the hood. And I'm emphasizing this point because when you're just starting out and learning about the EEG technology, you'll face a lot of formats and encodings that could be intimidating at first. And a lot of times you have very limited access to the equipment, so you don't have a lot of time to exactly figure out what is going on. So for example, you'd start with a device like OpenBCI, Emotiv, GTEC, Muse, and you end up with files written in very specific formats that ultimately need to be converted to another format that your signal processing environment prefers. So for example, we're focusing on OpenVibe here, which records in its own .ov format, but can also work with CSV. But there are also other environments such as MNE, which if you go to their website and look into the different formats they support, you see all these different ones. Well, mainly you have the EDF format, the European data format. Then you have BDF, GDF, all these different ones. And to convert them, there are converters out there, such as the EDF browser, which we have here. And it has all these different formats that it can convert to and from. Again, you see EDF and BDF and EDF Plus. And if we go to their website, EDF browser, free open source toolbox, intended for but not limited to time series storage files like EEG, EMG, ECG, bioimpedance, etc., which are all also technically the same in storage. So it's been around for a while, and it's built around the EDF format, first and foremost, which is the original, or at least like one of the earlier storage formats that became a standard in 1992. And if we zoom in here, it describes it as one data file contains one uninterrupted digitized polygraphic recording, which is a great description for what the nature of what these files are storing is. For example, here's an image from the book EEG Primer by Fish and Spellman that shows an analog setup of what an EEG recording is. So you have your amplifier, and the signal goes through, you have your high pass filter, cuts out the low frequency, and then your high frequency filter. And we would have a 50 or a 60 hertz band pass filter, and the writing unit, which back in the day used to be oscillating pen, but now the same voltage is measured in time, sampled, and quantized, and the result is stored as a table like the ones we've been working with thus far. So that's what they mean by polygraphic recording, or digitized polygraphic recording in our case. So let's continue. A data file consists of a header record followed by data records. And if you scroll down here, you can actually see that header, which contains text information about the file and the recording and the patient and the equipment used, and all very important information, but mainly the sampling frequency and the unit the file is recorded in. And then it is followed by the signal after it. So in essence, it's really no different from what we've been looking at thus far. The main difference is that in our files, in a CSV file, your signal is also stored as a text file, but here the signal is stored at a binary format. Let's look at another format. For example, here BDF. Here, BDF Plus is the 24 bits version of EDF Plus. And the idea behind BDF Plus is that EDF Plus software can be easily modified to accept it because the headers are the same, only the sample size of the data part increased from 2 to 3 bytes per sample. So structurally, no different from our CSV file or EDF for that matter. And the plus part is about being able to contain more patient information in the header and containing annotation events, which is really the main technical difference between all of these formats and how they can store markers, which we'll talk about later. So the point I'm trying to make is to not be intimidated by all of these different formats. They're all basically, again, table data with different headers. So for example, you have XDF here, which is the new kid on the block, which is a format used by the lab streaming layer communication protocol, which is trying to become the standard for simultaneous signal recording from multiple devices for multiple sampling rates. Here you can see their project. And a lot of environments are actually starting to support this. So it's becoming more and more popular to be used in different experiments and environments. And if you want to use MNE, for example, to be able to use all their beautiful academic visualizations that you can easily generate, it says here that MNE Python does not support loading XDF files out of the box. And this is a good example of the type of small issues that can really stop in your tracks. So MNE does not support loading XDF files out of the box because the inherent flexibility of XDF format makes it difficult to provide a one-size-fits-all function. However, it is relatively straightforward to import only a specific stream, such as EEG signals, using the PyXDF package. See this link, and a more sophisticated version of MNE Python called MNE Lab is also able to import it. But now you have to go and learn another new package that may or may not work as you expect. Look for a converter that can convert your file directly to something that your target environment can understand. But you don't need to worry about that. As long as you have access to the raw tabular information in form of a CSV file or any other way, and you can extract it from that format, the other formats can use it to build their own raw file, or you can just copy their header and other peripheral information as boilerplate, as you saw earlier that we did. So for example, for MNE even, you are able to build the raw file from scratch. We look up raw scratch. You'll see that the structure has an info object, which is the header, and the raw object. And these two, well, by this point, you'll have your raw object. So here it's where it makes its header. And here's where the raw object is made, which starts from a NumPy array. So it's just another table of floating point values, floating point samples that we're basically adding another header to. And at this point, the raw array, the raw file that MNE can understand is made. And from there, you can add annotations and epochs, but the heart and soul of it doesn't really change in between all of these formats and all these different extensions. As long as you have access to your samples and you know your sampling rate and you know what unit it's been recorded at, because, for example, MNE prefers volts, whereas OpenVibe prefers microvolts, which the difference is only a decimal point, but it's something you need to be aware of. But the focus of this video is on OpenVibe, and we're going to make our own file from scratch now. And the files that we're going to convert are these two long recordings from two different motor imagery recording scenarios. One is recorded using the Emotiv Epoc X. And let me copy it here. And the other is recorded using the OpenBCI system, which is, if I'm not mistaken, recorded using OpenBCI's own GUI. So we're also going to copy this. And for reference, I also have a file from an OpenVibe motor imagery scenario, the one that we're going to continue in the next video, but it's recorded using the same setup that recorded our OpenBCI file. So we're going to mainly use this as a reference, but you can see that it actually has some elements in the last three columns that our initial file doesn't have. So these are the markers, and they're very important when it comes to a lot of biosignal processing, because these give context to the signal that's already recorded. Well, let's just rename them so we can tell them apart easier. And we're going to name the OpenBCI 1A and its reference AREF, and the one from Epoch X we'll call B. And this is the OV OpenVibe file that we don't need. So we're going to take the signal from A and use AREF as a reference and create a new file. Let's call it A converted. And it could be .text or .csv. I'll just choose .csv for it. And we need a spreadsheet program to edit our files. So it could be Excel or Google Sheets. I'm going to use OpenOffice since it's free and available. What I'm about to do here is very easily scriptable in Python or using NumPy or any other programming language you might know. Even if you're not good at programming and you're just starting out, this is in essence text manipulation, which is one of the first things you learn in programming after Hello World, is to open string files and move characters and split them and add them. So this will be actually a great practice to see if you can use what you learn to solve a problem. Let's go ahead and look at our file. When you open a CSV file in most spreadsheet programs, it often asks you to designate how each column is separated by. Although the file might be CSV and it could assume that it's going to be separated by a comma, it can also be separated by other characters such as a tab. So if you actually record a raw file through the OpenBCI GUI, it gives you this text file, which is the one that we're working on. But it also saves a CSV file from BrainFlow, which is the underlying framework that's running the OpenBCI GUI. And if you look into that, although it's called CSV, you can see that they're not separated by commas, but they're actually separated by tabs. And well, you can't see them here, but if you open it in Visual Studio Code, for example, yeah, you'll see this arrow that's indicating that this is not a space, this is a tab. So it'll ask you a question about how each column is separated, and if it looks good here in this preview, that means everything is good. Although we might have these extra rows, but nothing should be a problem. All right, so that's A. Let's also open our other files. We had B from Emotiv Epoc X, also comma separated. And we have our reference for A, which was through OpenBCI. And we also had an empty file. We can just start with this, or I can just, so we created this CSV file, which is an empty text file. We can open this, or we can just open an empty file like this and save it as our file. So CSV, I'm just going to do this to show you what I mean by delimiter, and place it, yes. So here is where you set the options that you'll have to set when you're opening the file as well. So the text encoding, because it is a text file at the end of the day. And here's where you can pick which kind of delimiter or separator your file is using. Could be a comma, semicolon, colon, tab, or space, and hit OK. Yes. So if I Open our file again. It's an empty text file, although it does have some size because now those encoding headers are added to it. But other than that, it's just an empty text file. Now, let's take a look at our files. So we have A. So this is A, which is a file that's recorded through the OpenBCI GUI. And let's just quickly compare it with its text counterpart. So A. So first thing you might notice is that the numbers have changed a bit. So they're shorter now. Here you have 3.0, but here you only have 1, 2, 3 without the fraction. We can go ahead and do the same for our reference file. If we open it in the text editor, like VS Code, yeah, here it's more apparent. So we have all these extra characters that have been truncated here. And the reason is that, again, these are not numbers. These are characters. This is not the number 0, this is the character 0. And the spreadsheet program has to first convert these to numbers. And when they're numbers, it'll choose how it shows them, so I can actually change how they look like. From here, format cells, you can add decimal places, so like 10, and have them look like that. But they're not actually stored like that. They're stored as floating point numbers, and they're just shown this way to us. But here, these are the characters that the numbers are saved at. And a lot of times you'll see in CSV files that they do this because it's better to have the same number of characters if you're dealing with a text file. So for example, if you know that your first column is always 10 characters, you'll know that you can just go 10 characters forward and reach the end of first column. So it's useful for automation and scripting later on. But here we're making our file from scratch, and the goal is to get this file A and make it look like our reference file, aref, minus the markers, which are subject for another tutorial. All right, so both of these files are recorded using the same device. They're both recorded at 250 Hertz, and they both have 8 channels. So here we have 0 to 7, and here the channels are named after the head position or the scalp position that the electrodes are at, which is what's most common with EEG files. But here we also have 8 channels, 8 columns of data, plus the 3 extra columns that we'll just add the headers for. But other than that, the signal part of our data basically stays intact. So we can just copy our channels. These are going to be steps that you're going to repeat in a script as well. So you probably pick out the columns that you need. So here, channel 0 to channel 7, our signal. And we go to our empty file, and we just paste them here. All right, so we don't need these rows. Let's get rid of them. Oh, delete rows. All right, so this represents the empty array, empty variable that you're copying the data to and manipulating. So we just picked our channel columns, our signal columns, and copied it to our new empty file. And we're pretty much done with the original file. We can use these timestamp and index columns, but let's just do it from scratch, and then I'll show you some tricks. So first of all, we need these 2 extra columns, 1, 2, for our time column and epoch column. And we can go ahead and copy the header, but let's say we don't have a reference header. So it's capital T time, IME, colon, your sampling rate, which is 250, and capital H and small z for Hertz. And epoch is just capital E-P-O-C-H, epoch. And I'm just gonna copy the header from the last 3 columns. But you can also use the reference I mentioned, the CSV file format description file, and just copy these 3. But you can just go ahead and also type them in. All great solutions. All right. So how are we going to create these columns? Well, there are a lot of creative ways actually to achieve this. I'm going to use a spreadsheet way. So I'm going to add another extra column here. And, you know, in any spreadsheet program, you can just write a series, and if you pick the last one and click and drag that corner down, you get the rest of it. But it's going to be difficult to drag it all the way down if it's a large file. So I'm going to show you how to navigate it. So you can use Control and arrow keys to jump to the next element in the table. So left, right. And if I press down, it jumps to the last element, last contiguous element in this column. Here I release Control and I go left, 1, 2. And now again, I hold Control and Shift, because Shift selects up and down. But if I hold Control, it will jump all the way up. Now let's do that again. Control Shift up. All right, now we have this column selected. Can deselect the first one. So hold Control and click and go to Edit, Fill, Series. And this does the same thing. So direction is down, start value is 0. We don't know the end value, and just increment by 1. All right. Now we have a linear series that is incremented by 1, basically a long index for our file. And we're going to use a function here. So if you remember, I said that these timestamps are generated based on the frequency, the sampling rate, basically 1 divided over the sampling rate. So we can basically do a division of this column over the sampling frequency and get basically the same results. So here we can just write equals, and you can just reference the cell next to it, which is A2, and divide it by 250. Hit OK. So it displays 0, but if you see here, it's actually a formula. So if we copy this cell, so edit, copy, and let's go ahead and select the rest of it with the same trick. So, and if I paste it, it automatically continues from A1 to A2, sorry, A2 to A3 and all the way down. So if we compare it to our reference file, let's see, the, I don't know, 416th sample. Is it the same one here? Yep. We have 1.655, we have 1.656. These are going to be similar in the end anyways, but yeah, this is the results. It matches our reference. So that was pretty easy. You can also format it to have more decimal places, so it would kind of represent what we see here. But yeah, OpenVibe isn't super strict about these, at least for reading. But what it is strict about is the epoch column. So if you remember, the acquisition server is where it's decided what this column look like, but you're free to pick any of these numbers. So normally it was 32, but there's 64, 128. As we can see in this file, this one changes at, so yeah, 129. So this one was recorded using 128 sample chunks. But we can pick 32, 64. Let's go with 32. So the way we're going to do it is similar to the way we did the timestamps. So we divided this column by our sampling rate. So if we go down to the 250th sample, this is where the timestamp crosses 1, and this is where zeros turn into 1. So you basically have that number of zeros, that number of fractions before you turn into a whole number. So that means if I can find a way to just get the integer part or the whole part of the division, then I will have what I need for my epoch column. So, well, let me show you. If I do what I did here, which is equal A2 divided by 32, or chunk size, hit OK, and I can drag this down, or I can just double click on it. So you'll see that I have all these sub-zero fractions. They're just growing by 1/32, which is this number. And at the 31st sample, which is this 32nd in total sample, it switches from 0 to 1, which is 32 divided by 32. And then it's 1 all the way to 64, then so on and so forth. So if I could keep just the integer part and get rid of the fraction part, I will basically have what I need for my chunk structure. So we do that using the quotient function, both in math and here. Quotient is basically the other side of modulo. So modulo will give you the right side of the decimal, the fraction, and quotient will give you the whole part. So here we can just Q, yeah, there's only, and numerator would be the index column, and then the denominator will be 32, our chunk size. And now if I continue this down, there we go. So we have zeros all the way here, and then 32 to 63 and 64 to all the way down. So here actually you see that my chunk isn't complete. And I'm just going to leave it here to show you how OpenVibe really doesn't like it, and it will throw you an error if not crash out completely. But our file is basically done. So we have to save it as CSV. That way it's going to just save it as a text file and going to remove this formula when it's saved as a text file. So let's just scroll up. Oh, we need to remove this column as well. Well, we'll do it after we save. So it's file, save. Let's just look at the file as it is. All right, other than the extra column, everything else looks good. So let's get rid of that as well. We need to close this and open it again. So it has to convert it back from CSV without any of the formulas. And there you have it. Now I can just delete this column. And now this should be a file that's readable by OpenVibe. So let's save it and try it out. So this is our file, A converted. And this is the file reader box that we used. And I'm gonna disable the file writer, although it's interesting to see how it will output next to our file. So A converted through OpenVibe. Oh, caps lock doesn't matter. Apply. And but if we press play, there we go. Everything is working fine. So we just converted a whole different 8-channel raw recording from another system, from the OpenBCI GUI to an OpenVibe friendly format without doing a lot of work. And we basically generated our own timestamp and everything else. But if I fast forward, yeah, there we go. So it will exit the scenario and throw an error. And it says that missing data in file may be corrupted, details chunk is not complete. So we can actually go ahead and fix that. So let's see, we can do it in a text editor as well, because it's only the last that are affected. So here we see 493. All right, so we just have to get rid of all the samples after 492. And this way we will not receive that. Let me just save it as another file then. Converted, chunked. All right. And now if I open that, play, no problem. Fast forward, no problem. I mean, stops at the end, but doesn't exit because it doesn't have an exit marker, but it plays through no problem. All right. And now just to recap, let's just repeat the same steps for our Emotiv Epoc file, which we don't have a reference for, but again, we just need to know what the sampling rate is, and we're good to go for the rest of it. I know that this file was recorded on Emotiv Epoc X, so it is recorded at 128 Hertz. And it has actual custom timestamps, custom markers that the researchers added themselves. So it follows their own, it's basically a text marker, which I'm going to also convert to an OpenVibe marker in our next tutorial. But to convert this to an OpenVibe readable format, let's just, first of all, save it separately. CSV, so it'll be and again, we only need the signal channels, but I'm just going to actually make use of the timestamp and index channel that's left here for us. So first I get rid of these columns. And we can paste our header back from. These 3 columns have to be these. And these are the names from Emotiv Epoc X's electrode location. And for the time and epoch column, first of all, let me fix this 128 Hertz. There we go. And I can be smarter about this one. So these timestamps do correspond roughly to what they should be with a bit of irregularity. So if I just copy the first value, which is the first timestamp, and just select the rest of them and subtract it from the rest of the timestamps, I get basically the same relative timestamp that OpenVibe uses. So paste special. Here I can subtract, I guess paste all. There we go. And if I scroll up, there we have it. And let's also make a column for our quotient operation. So Q K2, and let's also go with 32. All right. Let's see. Yep, looks good. Now we just have to save this. So to sort of solidify this and get rid of the formula. But another way is to just click this button. This takes it out of edit mode. There we go. And if we go back to edit mode, now it's editable again, so now we can get rid of this column, but these are now numbers and they're not related to this column anymore. So you can just delete it and everything else looks good. Control S, save. And let's open OpenVibe and let's try our new file out. All right, so and let's change the file writer to another one because this is B converted. All right, and we hit play. Ah, some error. Let's find out why. So it's a location error. Let's see. It might be still open in here. Let's close this. Error in the header of the file. I made a mistake somewhere. Let's see what it is. Ah, Epoch doesn't have a name, doesn't have a header. I missed that, sorry. So Epoch, capital E, P-O-C-H, and the rest should be good. So Control S, save, and let's try this again. Okay, so it might be the fact that it doesn't like periods in the names. I'm keeping these crashes in because this is part of the process and things go wrong that you didn't expect that you should be ready to deal with. So if I just do Control F, EEG dot, and just replace all with nothing. Yeah. So let me save it. Saved. OpenVibe. And let's try again. Now it's working. So see, things crash, and it's really part of the process, and just kind of have to get used to it and be patient. All right, everything seems to be working. So this is the signal from an Emotiv Epoc X recorded using their own system, and the CSV file that you can get through their process. And now it's being read through OpenVibe, and now you can do all kinds of filterings and all that. And this is quite successful. So let's also check out the files that we just created. So we had A converted through OpenVibe. Let's open it with VS Code. And there you go. See, this is how it looks like when it comes straight out of OpenVibe through the CSV file writer. And if I split the one we made to the right and scroll up, yeah, so the one through OpenVibe, as you see, it has designated column sizes, although we could have done the same when we were saving our file using OpenOffice. That was one of the options. But other than that, let's check it. Let's compare our timestamps. So 50th line, 50th line. So ours is kind of rounded up, and OpenVibe is now a bit different. So this means that OpenVibe, every time it passes the file through, the timestamps are dumped and regenerated. So again, this is like good news, because that means you can easily regenerate it. But it'd be nice if it was able to also keep the original timestamps. But this is a very robust system, and it's easy to figure it out and make it work. It is sensitive to some bits of information, but that's really the easy part. And the tricky ones like timestamps and specific headers or formattings or encodings, none of them are available here. So it's quite a great system to work with and start trying out. But things aren't really well documented in the EEG world. But this is exactly why I wanted to make sure to make a basic tutorial, just very simply explain what all of these formats and all these different environments are expecting. Because when you understand how they work under the hood, you will have a much easier time to figure your way out when you get stuck. Because there are a lot of intricacies and not everything is well documented. So we now know how to convert any CSV RAW file to something that OpenVibe can read and work with. So in the next tutorial, I'm gonna continue going through the motor imagery scenario and go through the next stages, the acquisition, the training, and putting it online. And that's where we talk about markers and how to look at them, how to convert them, and how you can convert, in this case, signal from one motor imagery session on a different device and different system and convert it to one would then use OpenVibe's CSV probability and classification algorithm. So I'm going to show you how you're able to, for example, take a custom recording from a motor imagery scenario from another device, another system, but one that you have marked, and take it and convert them in a format that OpenVibe can understand and run it as if it was recorded through OpenVibe and get the probability and classification results that you would get from OpenVibe, so you can compare it with your own system. So that will be the topic of the next video, and hope you like this one. See you in the next one.